In this section, we're going to take a look at solving for sides or for angles in triangles when those triangles are not right triangles. Okay, so we learned how our trigonometric functions relate to right triangles and worked with that pretty extensively. But now we're going to kind of broaden the types of triangles that we can work with. So let's take a look at a kind of a real-world application as a starting example. It says two planes, one flying at 300 miles per hour, the other flying at 400 miles per hour, leave Seattle at the same time. If their courses diverge by 40 degrees, how far apart are the planes after 90 minutes? So let's just draw a little picture here. Okay, so let's say this little dot here represents Seattle. And so suppose over here I've got my 300 mile per hour plane, and then my 400 mile per hour plane, of course, is going to cover more distance, so I'm going to make it a little bit longer, and we're saying that this angle here is 40 degrees. So their question is, okay, after 90 minutes, right, what is the length of this side of the triangle here? All right, so what else do we know? Okay, we know this is what we want to find. We want to find this distance here. But what else do we know? Well, we know that this plane here is flying at 300 miles per hour, and we also know that 90 minutes have passed. Okay, and so if I've got 300 miles per hour, and I know 90 minutes have passed, I can multiply by not 90 minutes, but by 1.5 hours, which is what 90 minutes is, and that tells me how far this plane has traveled in that period of time. So that's 450 miles. And we can do the same thing over here. So 400 miles per hour times 1.5 hours. And so, of course, we get 600 miles. So put 600 right here. So I know these two sides of the triangle, and I know the angle between them. But this is not necessarily a right triangle. You might look at my picture here and say, oh, that looks kind of close to 90 degrees. And it may be close, but we have no reason to believe that it's exactly 90 degrees. All right, so how do we deal with this? All right, so let me go to the next slide for just a moment and then come back. So what we do is we use the law of cosines. So the law of cosines looks pretty complicated, but it's actually not too bad when you understand where all the parts come from. So let's just focus on this first one here. So if I have a triangle labeled like this, where the angle that's opposite of side A is alpha, that's kind of the A in the Greek alphabet. The one opposite side B is beta, and the angle opposite side C is gamma, then I can always figure out what A is by setting up this equation. A squared equals B squared plus C squared minus 2BC cosine alpha. So the first thing to note is that the side and the angle that are opposite each other are what appear in the formula. Right, so opposite each other. And then besides that, you just have the other two sides showing up in the rest of the formula. Okay, so we will talk about why this is true in a moment, but let's just go ahead and use it in the previous problem. So what the law of cosines says is that if I'm interested in D, I can say that D squared is going to equal squaring the other two sides that we know, and then subtracting, adding those together, and then subtracting off 2 times one side times the other side times the cosine of the angle opposite the side we're interested in. All right, so there's a lot there, but it just becomes basically an arithmetic problem from here. So what we get here is if I punch these parts in my calculator here, these two become, let's see, 562,500. And then these parts here become, let's see, 540,000. And then we have the cosine of 40 degrees. But I know, of course, that what I'm interested in is d, not d squared, so of course I'll take the square root of all of that. And the reason I'm waiting on doing the full, I didn't push everything in my calculator right away, is because I know I want to take the square root, and I don't want to be taking the square root of a number that I've rounded, because that's just going to compound error for me. So typing all that in, making sure, of course, my calculator is in degree mode, what I get is 385.8 miles. And that's how far apart they are after that period of time. And, you know, but based on my picture here, that seems pretty reasonable. All right, so let's talk for a moment about why it is that this is true. I mean, it's kind of perhaps seems like an outlandish sort of formula. So the way to kind of convince ourselves of this is to go ahead and make what's familiar, make a right, basically two right triangles out of this big triangle. So let's call this h right here, h for the height of the triangle. Okay. So on the one hand, we know that this entire length here is b, but I want to break it up into two pieces. So let's call this side right here x, and that's going from here to here. And then the rest of it, well, if it's the total is b, then the rest of this would be b minus x. And so now that we have right triangles, we can talk about the Pythagorean theorem. So what I'm going to do over here first is to say, with that left triangle, I know that h squared is equal to the hypotenuse squared minus this side squared. And I also know, if I just look at this triangle down here, that h squared is equal to a squared minus b minus x squared. Okay, well, if both of those things are equal to h squared, then of course they're equal to each other. So I can say that c squared minus x squared is equal to a squared minus, and I'm going to go ahead and expand that out, b squared minus 2bc, excuse me, 2bx plus x squared. And then if I distribute that minus through, we get minus b squared plus 2bx minus x squared. All right, and so one thing I can see is that right off the bat, those x squareds go away, and that's good because x is not one of the sides of the triangle. So the less x's I see, the better. All right, so let's see what we've got here. What I'm trying to do right now is I'm trying to basically derive this first version of the formula. So what I'd like to do is have a squared all by itself. So just by doing a little bit of manipulating and moving the minus b squared and the 2bx to the left side, I can do c squared plus b squared minus 2bx is equal to a squared. So this is already looking quite a bit like this formula up here. The only difference is, instead of an x, we have a c times the cosine of alpha. Okay, well, let's think about that for a second, though. Okay, this x right here Okay? This x right here is the side of a right triangle. So I know that the cosine of alpha is equal to x over c, which means that c times the cosine of alpha is equal to x. So all I have to do here is replace x with c times the cosine of alpha, and I have that first version of the formula. And of course you can get the other two just by setting up this triangle a little bit differently. All right, so this is the law of cosines, and like I said, it might seem like a lot to memorize, but really if you can just remember the side that's isolated and the angle opposite of it are what you're going to involve in the formula, then the rest is pretty easy to remember. All right, so let's apply this to a different situation. If you recall from the first example, we knew the angle between two known sides, and we used it to find the opposite side of that angle in a story problem. So in this one, we know all the sides, but what we're looking for is the angle. Okay, so what the law of cosines would say is that I would take the side opposite the angle, set that equal to the square of the other sides added together, and then subtract 2 times those other two sides times the cosine of, this time I don't know my angle. So lots of big numbers here, but at the end of the day we have one unknown, which is the angle, but we know everything else, so this should be very doable. So we can go ahead and start working this out. On the left here, this is 388,129 is equal to, and I'm going to put these together in one step. Those two become 811,249 minus, and then this all becomes 574,080 times the cosine of our angle. All right, I'm going to just have a little equation to solve here. So if I subtract 811,249, 811,249, then on the left side here I've got negative 423,120, and that's equal to negative 574,080 cosine of theta. So moving over here, that means that the cosine of theta is going to equal this quotient. And again, I'm not anxious to plug this into my calculator because I know I'm going to have to take the cosine inverse of this, so let's just leave it alone. So we know that theta should be the inverse cosine of that fraction, and of course I'm going to drop the negatives because alright, and so whatever that is, so again let's make sure we're in degree mode here, and if we're in degree mode this gives us 42.5 degrees. All right, so let's take a look at one more example here. It says find the missing sides and angle in the triangle below. And this, by the way, is known as solving the triangle. Okay, so anytime you hear the language solve the triangle, that means find all the unknown parts of it. So if we look at this, I think there's a clear place to start, and that is with the angle, okay, because I already know two of the angles. So just right off the bat, I can figure out what this angle is because I know that every triangle, the angles have to add up to 180 degrees. So I can say 180 degrees minus 40 degrees minus 35 degrees. And that gives me 105 degrees. So I know this angle here is 105 degrees. All right, so that's good. So I'll maybe just put that in there to make it clear that I know that angle. Okay, so if I want to find the other sides, let's think back to the law of cosines for a second. So backtracking just for a moment. So the law of cosines looks like this. And so what you notice is that the formula has one angle involved, but in order to find any of the sides, you need to know both of the others, right? So in order to figure out what a squared is, I need to know what b squared and c squared are, okay? So if you have two of your sides being unknown, then the law of cosines cannot be used. All right, so what do we use? Okay, so on the next page here, let's take a look at this. This is the law of sines, okay? And what it says is that the ratio of the sine of your angle to its opposite side is always going to be equal to the sine of a different angle to its opposite side. Okay? So all of those ratios are equivalent within any triangle. Okay? So let's see how we would put this into practice here. Okay, so I know this 54 feet, and now I know this 105 degrees. So what I do know is that the sine of 105 degrees divided by the length of the side opposite to that should be equal to the sine of 40 degrees divided by a, if I call this opposite side here a. That's what the law of sines says. And so now we just have this little proportion to solve here. And so we can multiply both sides by 54a, or if you recall from some of your algebra days long ago, you can think of it as kind of cross multiplying across that equal sign. So at either way you think of it, you get the sine of 105 degrees times a is equal to 54 times the sine of 40 degrees. But then to get a isolated, we have 54 times the sine of 40 degrees, all divided by the sine of 105 degrees. Okay, and so that gives me an approximate answer of 35.9. Not exact, but approximate. Okay, so that gives me A. And now that I know A, I suppose I could use the law of cosines if I want, but when possible, I'm kind of partial to the law of sines because it's just kind of simpler and it's easy to remember. So to find our other side here, to find B, then we'll just go ahead and set up another law of sines. And so again, I'll just use the sine of 105 degrees divided by 54. And that's going to be equal to the sine of 35 degrees divided by B. So B times the sine of 105 degrees is equal to 54 times the sine of 35 degrees. And again, this sine of 105 degrees is just a number, so I didn't really show it very carefully in the last one, but all I'm doing is dividing both sides by that. So those cancel out. And so I get that B is approximately equal to 32.1. So now I know every side of this triangle, I know every angle, so I have effectively solved the triangle. All right, so let's just talk briefly about why this makes sense. This one's even easier to understand than the law of cosines, but I'm going to just play the same game. I'm going to go ahead and make a right triangle here. Well, two right triangles. I'll go ahead and call this H. So this time, what I'm going to do is I'm going to use the fact that the sine of my angle is equal to the opposite over the hypotenuse. Okay, so I know that the sine of alpha is equal to h over c, which means that c times the sine of alpha is equal to h. And then over here, I can do a similar thing. I can say that the sine of gamma is equal to h over a, and so a times the sine of gamma is equal to h. So they're both equal to h, so that means I can say that c sine of alpha is equal to a sine of gamma. But the law of sines is much easier to remember if you can think of each fraction or each part in the equal sign involving the angle and its opposite side. So rather than memorizing it this way, we'll divide both sides by c times a, which allows those to cancel and then allows those to cancel. And so you can see you're left with the sine of alpha over a equals the sine of gamma over c. And of course I could do the same thing with beta and b if I just drew my picture a little bit differently. All right, so just to kind of summarize here, when we're solving triangles, really we're going to have four scenarios to think about. So if you know one side and two angles, okay, then you're always going to use the law of sines. So that's whether that's angle side angle or you know side angle angle, either way you're going to use the law of sines. And remember, that's because you can't use the law of cosines because you need to know at least two sides to use the law of cosines. Okay. Now there is one situation where you definitely need to use the law of sines even when you know two of the sides, and that's when you have side-side angle. Okay, so if let's say I knew B, C, and beta, if those were the three that I knew, that would be side-side angle. That one you must use the law of sines. Or I guess you could. I guess you could use the law of cosines, but it's a lot harder. Law of sines is really is definitely what is best. And here this is known as the ambiguous case, and we're going to explore this in class together. But the ambiguous case means that there may be more than one triangle that satisfies the side, and angle that you're given. Or there may be no triangles also. So it's kind of a weird case, and we'll talk about that a lot in class, but we will use law of sines for that. But if you know two sides and the angle that's between them, okay, so just using a different color, that would mean if I know these two and the angle between them, then law of cosines is what we want to use. That's what we had in the very first problem with the airplanes and figuring out how far apart they were. Then we use the law of cosines. And then if we know all three sides, then also you need to use the law of cosines.